Okay, I'm going to give this a shot. And just in case it does not work, I at least have a backup video that I made last semester. Lesson 15 and part of 17, I wanted to go over with y'all today. Lesson 15 deals with extreme values of functions on closed intervals. And I'm just going to read this verbatim off the screen. In the past, when virtually all grading was done by hand, often laboriously, derivatives were the key tool used to sketch the graph of a function. Now we can graph a function quickly and usually correctly using a grapher like a graphing calculator or a website like Desmos that makes graphing a whole lot easier. However, confirmation of much of what we see and conclude true from a graph review or a graphing website or app must still come from calculus. In other words, we may want to see if our graph has a maximum point or possible minimum point, or areas where the graph is increasing or going up the hill, or decreasing or going downhill. So derivatives still help us determine the behavior of a function. This lesson shows how to draw conclusions from derivatives about the extreme values of a function and about the general shape of a function's graph. We will also see how a tangent line captures the shape of a curve near the point of tangency. Actually, we won't go into that part, but mainly we will go over how derivatives can predict the behavior of a graph of a function. First thing we need to know is extreme values of functions, or otherwise known as absolute or global extreme values. One of the most useful things we can learn from a function's derivative is whether the function assumes any maximum or minimum values on a given interval, pardon me, and where these values are located if it does. In real life, we also use absolute or global extreme values to figure out, for example, the most effective size for a dose of medicine, or what is the least expensive way to pipe oil from an offshore well to a refinery down the coast. Graphically, this is what we're dealing with. You have a curve over a closed interval from A to B. Now, I'm just drawing some random curve here. Now, the lowest point is called the absolute minimum. And the highest point, which is somewhere right here, is called the absolute maximum point. Definition of absolute extreme values. Let f be a function with domain capital D. Then f of c is the a absolute maximum value on the domain if and only if your function f of x is less than or equal to this f of c. In other words, right here, here's f of c at the very top, and here's f of x, which is below. So if f of x, so the curve is below this f of c, then we have an absolute or global maximum point. You have an absolute minimum value if and only if your function f of x is actually greater than or equal to this f of c. To illustrate that, here's f of c, our minimum point, or excuse me, possible minimum point. On both sides, our function f of x is above f of c. That means our function at this point is greater than or equal to f of c. So because all of that happens, then that means we have an absolute minimum point down there. You can find absolute extrema not only graphically, but algebraically. And let me go over the steps with you. Step 1, find all critical points of f on the interval. A critical point is when your first derivative is 0. So that's how you find all your critical values. You may have one or more than one. You take your first derivative of your function and then set your first derivative equal to 0 and solve for x. Step 2, evaluate f at all critical points and endpoints. So whatever our critical point is, plug it into your original function. And whatever your endpoints are, you also plug them into your original function. And then the last step, take the largest and smallest of these values. The largest indicates absolute maximum point. And the smallest value out of everything you plug in indicates an absolute minimum point throughout that interval. All right, let's look at the first example, example 2. Find the absolute maximum and minimum values of f of x equal to x squared on the closed interval -2, +1. The first step is to take the first derivative. So our first derivative using the power rule is just simply 2x. The next step, which is actually step 1 in our list over here, find all critical values or points of f. So to find your critical point or points, just set your first derivative equal to 0 and solve for x. So when we divide both sides by 2, our lone critical point is x equal to 0. Now we are ready to find any possible absolute or global max or min values. So let's plug in our critical point first into our original problem. So that equals to 0. And we also have to plug in our interval endpoints also. So we'll plug in -2 first. And that gives us a +4. And when we plug in +1 into our original function, that gives us +1. Now we can determine the absolute extrema. Out of all three answers, 0 is our smallest value. So 0, or x equal to 0, is our absolute minimum. And 4 is the largest answer we got. So x equal to 4 is your absolute maximum. Now I want to pull up Desmos and show you guys that all of this information is correct. So just 1 second, let me pull up Desmos. And type in our function, f of x equal to x squared. And we're only concerned with, let's see, let me snip this and put it on our paint board. Or actually, I can do it here. I think we were going from -1 to, I'm sorry, -2. Erase that. We're only concerned with the interval from -2 to +1. So between -2 and 1, we have 0. It says the absolute minimum occurs at 0. And an absolute maximum point occurs at -2. Well, when you compare it with the value that we got for +1, which was this point right here, and at -2, it was all the way up here at +4. So +4 is higher than +1. So that means, and I'm sorry I can't see it on your end. Let me share this. Hold on just a second. Okay, there we go. Sorry about that. When we plugged in -2, we got +4. And when we plugged in +1, that gave us 1 also. Our absolute maximum occurs at -2 because 4 is higher than 1. So that is where our absolute maximum, as we predicted, will be, and also predicted correctly. X equals 0 is our absolute minimum point. Let me make up an example and we will go over it. Give me 1 second. Let me clear my board. Given f of x equal to negative 2x squared, going from negative 2 to positive 2. Let's do the same interval, negative 2 to positive 1. And we need to determine the absolute extrema, maximum or minimum points, if they exist. So the first step is to take your first derivative. So that would be negative 4x. The next step is find your critical point or points by setting your first derivative equal to 0. So when we solve for x, our only critical point is x equal to 0. Now we're ready to plug in not only our critical point, but our endpoints in our interval to determine where any extrema exist. So let's start with our critical point, x equal to 0. And we plug 0 into our original function. And that still gives us 0. Plug in our first endpoint, negative 2. Negative 2 squared is a positive 4. Times negative 2 gives us negative 8. And now let's find the value when we plug in positive 1. So when we plug in positive 1 for x, we get negative 2. Now, out of these three answers, the smallest is negative 8. So that is where our absolute minimum occurs. And 0 actually is the greatest value out of all three answers. So at x equals 0 is our absolute maximum point. In just a second, I'm going to switch to Desmos again. And we'll see if all this information is correct. All right, so let me share our web browser again. And our function this time around was negative 2x squared. And let me snip this and then I'll share it with you guys. Okay, we're only concerned with the interval from -2 to +1 again. If I recall, -2, its value is somewhere 6, 7, right here at -8. And when we plugged in 1, we got -2, I believe. And that's right here. Okay, since -8 is less than -2, then in this interval, we're correct. At x equal -2, that's our absolute maximum. And also correct, x equals 0 is at the very top of the parabola. So in this interval from -2 to 1, that is our absolute maximum point. So this is the only time you have to worry about absolute maximum or minimum points is when you are given a function and you are given a closed interval. Okay, let's go back to our notes, and I want to talk with y'all about the other type of extreme values. So let's see here. Hold on just a minute. Okay, let me zoom in so y'all can see better. Okay, there are extreme values known as local or relative extreme values, or local or relative extrema with an A. Now, I don't think I have the graph that they are referring to. The only difference between absolute extrema and local or relative extrema is that with local extreme values, your interval or domain or you have no endpoints. You have an open interval. And let's see, just to illustrate what I'm talking about. You have a graph, usually labeled as f of x, that keeps going. The arrows let you know that it keeps going, and this is an open interval. So if we were looking for local or relative extreme values, then we could probably say this point up here, I'll just call A, could be a relative maximum point. Now, graphically, how you can tell that you got a relative maximum point is that it's usually at the top of a curve. And we could probably label this bottom part B as a relative minimum point. Usually in a graph of a function, the relative minimum point is at the valley or at the very bottom. So let's go back over here to our notes. Local extreme values. Let C be an interior point of the domain of the function f. Then f of C is a local maximum value. And we have the same parameters here as before. Your f of x or your function is less than or equal to this particular point, as I showed you on the general graph. And minimum point is where your function is above your minimum point, f of c. Local extrema are also called relative extrema. And the steps to finding a local or relative extrema, the only same step as before is you take your first derivative and find your critical points. So you don't plug in your endpoints because there aren't any here. Now, I wanted to go over, just to help with the next section when we cover it, I want to go over what the first derivative tells us. It tells us relative max or min points if they exist. We find our critical point or points if there's more than one from the first derivative. And the first derivative also tells us intervals if they're more than one, where our graph increases and or decreases. So let me just draw a general graph. Again, this is a graph, a function f of x, where we have an open interval, no endpoints. And we're just going to identify possible information. This top part up here, and you would prove this with calculus using your critical point, or finding your critical point. This would more than likely be your local or relative maximum point. And this point down here, dipping at the very bottom of your graph, is more than likely your relative minimum point. Now you can also, we'll do this in a separate lecture, you can also find the intervals where your graph increases or decreases. Now let me show you in red parts where our graph increase. This little part right here going uphill, and this little part right here going back uphill from the relative minimum point. All right, in blue, let's highlight the intervals that are decreasing. There's only one specific interval, and that's in the middle. Decreasing means you're going downhill. So that would be the interval on which your function is decreasing. In a separate video lecture, I will discuss the calculus way with critical points, how to easily find all of this information.